Hi folks, we are on the Unit 3, Day 9 lesson. It says Day 9 and 10, but really that just means that it's one very long lesson and then you guys would typically have a work period to complete the homework on this. So it's going to be a longer lesson today, but this would be normally a 2-period amount of work to cover. So we're going to talk today about how 3 planes could intersect, and sort of like 2 planes or the lines intersecting with planes or other lines. There's different cases to look at here, and in these ones there's actually going to be 8 different cases, so it gets to be a little bit cumbersome to kind of imagine all of them. As you will see, there's a lot more options of things that can happen. A number of these cases are just going to be pretty trivial though, like they will be situations where some of the planes may be parallel or coincident and are going to be more similar to the type of solution that we had when we had the intersection of 2 planes. There's 3 really kind of interesting cases of what could happen when you're trying to solve for intersections with 3 planes though. So again, I already said this, we've got 8 different cases, and we're going to group them into 3 general cases based on what the normals of the planes look like. So the first 3 cases are grouped into the situation where all 3 normals are collinear. So we're always going to want to take a look at the equations of these planes if in Cartesian form. So we should have a really clear view of the normals. If you were ever trying to find the intersection of planes and you didn't have the equations in Cartesian form, we're always going to convert all of the equations into Cartesian form. So the different cases where we're in this situation and we have all 3 normals are collinear or scalar multiples, the first case could be that all 3 planes are parallel. So here you might have 3 parallel planes and they're all different. And I'll give an example of that. So if, for instance, we had 3 equations and it was x plus 2y plus 3z plus 10 equals 0, and maybe x plus 2y plus 3z plus something else, 17 equals 0, and x plus 2y plus 3z minus 4 equals 0. So we can see all 3 of these normals are going to be collinear. We have the same normals for each, and the d value are all different. So these are not the same plane, but they all are parallel to each other. So that's case number 1. Case number 2 up here is 2 planes are coincident and the third is parallel. So a situation like that might be if we had, say, this x plus 2y plus 3z plus 10 equals 0, and then maybe another equation was just given kind of in a bad form and maybe was like 5x plus 10y plus 15z plus 50 equals 0. So you can see that that's actually the same equation, just not in standard form. And then this third one might be parallel, and you might have x plus 2y plus 3z minus 8 equals 0. So a totally different d value. So you can see that these 2 planes, number 1 and 2, are the exact same. And the third one that you have there is different. Okay. The third case where all of the normals are collinear would be all 3 planes are coincident. So in this case, we might just have three equations where they were all actually the exact same plane. So that one's just kind of times 2, and maybe we have 3x plus 6y plus 9z plus 30 equals 0. So you can see that these are all, they're not in standard form, but they're all actually the exact same plane. So for this one here, we have no, for the first two cases, we have no intersections. There's no spots here or here that lie on all three of those planes. There's no points that lie on the three planes in there, number 1 or number 2. But in number 3, we actually have infinite points of intersection because they're all coincident. It's all points on the plane. So the first two cases have no solution, and that third case has an infinite number of possible solutions. So that's all kind of grouped into the first type, where the three normals are collinear. The next type, which we're going to call case 4 and case 5, are where two normals are collinear and one is not. So here, the first one in this group would be case number 4 out of 8. That would be two parallel planes, third plane not parallel. And as you can see, there's going to be no solutions here. Because these ones would not have any points that lie on all three planes simultaneously. So what would that look like in terms of the equations? You would have two planes where the normals were collinear or parallel, but they're not the same plane. So you might have, say, like the x plus 2y plus 3z plus 10 equals 0, and x plus 2y plus 3z minus 5 equals 0. So those are my two parallel planes, and the third plane could be anything else, but it's not got a collinear normal to these ones. So it might be 5x minus y plus 2z minus 1 equals 0. It could be anything as long as the normal wasn't collinear with the first two. So that's case 4. Case 5 is where two planes are coincident and the third passes through them. So this is really just the same as having the intersection of two planes. You have a third plane that's just the exact same as one of the other two. So this is going to have infinite number of solutions. It will intersect on a line. So this is going to be solved the exact same way that you did on the day 7 lesson. I'm just going to put use intersection of two planes, because that's really what it is. You're just not going to use one of the planes that's a duplicate of the other one. So here we might have had the x plus 2y plus 3z plus 10 equals 0, and maybe we had that same plane but just written in a different form as 2x plus 4y plus 6z plus 20 equals 0. You're just going to pick one of these equations because they're really the same and solve for the POI of that with any other plane. 3x minus y plus 2z minus 1 equals 0. I don't know, I'm making up numbers there. So you have two planes exactly the same and a third one passing through it. We're really back to that day 7 with the intersection of two planes. So I know it's a little bit overwhelming to kind of say, oh my gosh, there's 8 different cases. That's a ton of cases to kind of know about. But really, we just sort of whiz through the first 5 cases. The last 3 are the ones where it gets a little bit more interesting and is probably what you're picturing if you kind of held up 3 pieces of paper or any flat surfaces and tried to figure out what those intersecting might look like. So the last ones are going to be where none of the normals are collinear. So none of these planes are parallel to each other, okay? And this is kind of what the diagrams are going to look like. So the 3 cases, I think we were on 6, 7, and 8. That's how I'm going to number those. Case number 6 is that there's no solutions up here. So each pair of planes intersect in a line. And for this one, there's no solutions because none of those points are going to be on all of the planes. And one thing that we would have to notice is that all of these lines of intersection are going to be parallel to each other. Otherwise, they would converge to a point. So the lines here do not intersect with each other. The next case is that all 3 planes intersect on a line. And that's, we're going to call case 7. And in this one, we're going to have infinite points of intersection. So, and we'll get to an example where I show you how we can figure that out if it's that case. The last case, and what you guys are probably, most people would picture if they were trying to intersect 3 planes, is case 8. And all 3 planes are going to intersect in a particular point. So here there's one actual solution where that one point is on all 3 planes. So here the planes intersect in a point and there's one POI. So that's I think what most people think of as the main case that can happen, but there's actually a lot of other situations. So when we're actually going to solve these, the first 5 cases, you're not going to solve the same way. I always want you guys to check, do I have any normals that are collinear? If you have collinear normals, then you're going to determine, based on what the rest of the equations look like, which of those first 5 cases do you have? And you are going to be responsible for either saying all of the planes are parallel, there's no points of intersection, or they're all coincident, there's infinite points of intersection, or noticing that maybe 2 of them are the exact same plane and doing the intersection of 2 planes. So all of those first 5, they're not going to be calculated the same way as the last 3. You're going to have to narrow that down based on which of the normals are collinear, and are the whole equations the same, or are they just parallel planes? If you get to these ones, we're going to actually solve these using the skills from the day 8, where we looked at solving matrices with 3 equations and 3 unknowns. So we are going to get into that in a little bit with some examples. I want to kind of discuss something about these 2 cases compared to this one. And it's a little bit hard to see in this diagrams for sure, but there's something special about the normals in case 6 and 7 compared to the normals in case 8. And if we were to draw, and this is going to be kind of a hard thing to picture, if I was to draw the normals of all 3 of these, I hope that you would be able to kind of imagine, and I will see if I can find kind of a better simulation of this, but hopefully you can kind of imagine what would happen if you put all of those normals tail to tail. Those normals are going to all be on a flat surface. They're going to be coplanar. And then same with this one. If I were to draw N1, and it's really super hard to draw three-dimensional things on a two-dimensional surface here, but hopefully you guys can kind of visualize this. I normally, when we're in class, I'll see if I can kind of do a bit of a demo with some real life objects. But these ones, again, all of the normals are going to be coplanar with each other, but in this one, they're not. In this one, the normals are going to form, like actually form the basis for space, because they will be going in different directions. So, and not coplanar. So there's actually a test for coplanarity, which sounds like it's not a word, but it is. So you can see that these normals are not going to be kind of scalar multiples of one another. And you can do this test to see whether it's going to be case 6 or 7. If the normals are coplanar, this would be N1, N2, and N3. It doesn't matter the order. You can do the cross product of 2 of them, any 2, and the dot product of the third with that cross product, you should get equal to 0. So if 3 vectors are coplanar, so I'm going to just kind of move this out and play with my markers here. If I have 3 coplanar vectors like that, they're all on this nice flat surface. If I did the cross product of any 2, so say I did the cross product of the blue and red, I would get this one that would be perpendicular. It's coming right out of the table. And then that one would also be perpendicular to the third one on the plane. So the dot product of this perpendicular cross product vector with the third one will be 0. So that's kind of a test for coplanar vectors. And you can do that if you are trying to determine whether something is case 6, 7, or 8. The problem is if you do this test and it is coplanar, there's no good way without trying to solve to actually figure out, well, is it 6 or 7? We can't narrow that down. So I don't normally do it. I usually just kind of trudge ahead and figure out based on the solution. But that can be a handy little check, and it's something that comes up in other applications of vectors as well.